Welcome again to this course on mechanics applied to aerospace engineering. This will be the first of 2 lectures dedicated to relative motion. After a quick introduction to relative motion, we will discuss how to describe the position and the attitude of one reference frame with respect to another. In this second aspect, we will cover a number of points which are particularly important. Together, when we have the position and the attitude of a reference frame, we can describe its instantaneous state with respect to another. But of course, reference frames can move, and they can do that in translation, but also in rotation, all right? So the second part of the lecture will be dedicated to discussing the angular motion of a reference frame, okay, covering aspects such as its angular velocity and its acceleration. Finally, we will close with a tremendously useful theorem to derive vectors in different reference frames, which is Coriolis theorem. Is to realize that different observers will describe the motion of objects in a different way. So in particular, they will not agree on the position, velocity, or acceleration of point particles, all right? Of course, as we have discussed in previous lectures, an observer can be assimilated to a reference frame, okay? So when we talk about observers, what we basically do is we are talking about different reference frames. So in this example, you can see 2 reference frames, okay, the red one and the blue one, and we have 2 observers, one on each. You can see that for the red reference frame, okay, for the astronaut on the red reference frame, the particle, the green particle, looks as a stationary object, okay, so its position is constant in space, its velocity is 0, its acceleration is 0. But of course, for the other observer in the blue reference frame, this particle has some motion, okay? So the 3 vectors are the position, velocity, and acceleration vector for these 2 observers are clearly distinct. So what we are going to do in this lecture is mainly trying to understand the relative motion of reference frames with respect to each other, okay? In the next lecture, we will discuss the motion of particles with respect to those reference frames. So what we need to do is to describe with much detail as possible 2 aspects of a reference frame. Remember that a reference frame, for example, S1, it's composed of 2 parts. It has the origin, okay, which is a point, and then it has a vector basis, all right? So basically we have to provide the information of the motion of these 2 objects if we want to describe the motion of the reference frame. So we will start with the easy part, which is discussing the position of the origin and how it moves, right? And then most of the lecture will be dedicated to the second part, to how the basis changes, okay? And this is what we call the attitude, okay? The attitude is the orientation of one reference frame with respect to another at a particular instant of time. Okay, so let's see how we can get started with this. So when we talk about giving the position and the translational motion of a reference frame with respect to another, what we mean is describing the position, velocity, and acceleration of its origin point. So imagine that we have 2 reference frames, S0 over here and S1, whose origin is point A. Basically, when we want to describe the translational motion of S1 with respect to S0, what we have to provide are these 3 vectors. So just as with any other point, okay, imagine a point particle P, if we want to describe the kinematics of a point, we have to provide the position, velocity, and acceleration of that point. So basically, that's what we have to do here. And if we give this information, then the motion of the origin of S1 is completely determined. As always, in relative motion, we can regard the things in reverse. So instead of trying to describe the motion of S1 from 0, we can think of the motion of S0, okay, here the blue reference frame, from S1. In this case, of course, what we have to provide is the motion of the origin O of S0, as seen from reference frame 1. Observe that although the position vectors are equal and opposite to each other, in general, the velocity and acceleration will not be the same, okay? The second aspect of the relative motion of a reference frame is clearly more complicated. So let us dedicate our attention to discussing the attitude. All right, so as I said before, the attitude is just the instantaneous orientation of one reference frame with respect to another. And in order to discuss this, we basically need to provide the orientation of the vectors of the basis of one with respect to the other. Okay, so imagine that we have a reference frame S1 and we want to discuss its attitude with respect to S0. Well, basically, what we need to do is to say what are these three vectors, the vectors of the basis of S1 in the basis of S0. All right. For the discussion of the attitude, it's important to remember that the origin of the reference frames doesn't matter. Okay, so we can separate the motion of the origins with the motion of the bases. So even if the origin of the two reference frames is different and the two reference frames are moving with respect to the other, we can always plot the bases with the same origin, and that will certainly simplify our understanding of the problem. Okay. So consider, for example, the vector I1. I1 is a vector that we can express in the basis 0, so we can basically project it along I0, along J0, and along K0. And the expression that we would obtain if we do that would be the one that I have highlighted here with a blue square. All right, there will be three numbers, these L with subindexes, which are the components of I1 in basis 0. We can do the same thing for J1 and K1, and we will obtain the expressions for the change of basis. All right, this is something that we already discussed in a previous lecture. So this is essential information that we need to provide if we want to establish or describe the attitude of one reference frame with respect to another. If we have the expression of the three vectors of one basis in terms of the other basis, we have all that we need to know. Related to this, there are, however, different aspects. For example, when we have a new vector, okay, any vector b, we will use these bases to express it and operate with it. So clearly, when we have more than one basis, we have multiple choices. We can describe that vector in one basis or in the other. All right, and as you know, this doesn't change the vector. The vector is just the same. It's just two different representations of the same vector. We saw in a previous lecture that these expressions are connected, okay? So the components in basis 0 and the components in basis 1 are not independent from each other, and indeed they are related. The way to see the relations is to use the change of vector expressions over here, okay, to replace I1, J1, and K1, and then gather the terms that are proportional to I0, J0, and K0 on the two sides of the equation, and we can find the relations between the components. These relations, we could write them in a matrix form, and that was the way that we introduced the change of basis matrix, okay, this R01, okay, remember that the numbers that we place here are just a mnemonic to remember that this matrix takes a column vector of components in basis 1 on the right and returns a column vector of components in basis 0 on the left. Okay, so you can see that the components, if you remember from the previous lecture, the components of this matrix are essentially the same numbers that appear in the expressions for the change of basis for the vectors of the basis, all right, except that they are rotated. Okay, so here I have highlighted in this red box the components L, x1, x0, and so on. Okay, and you see that these same numbers appear here in horizontal. Okay, so basically the numbers have been transposed. This is the matrix that you have to use if you want to use matrix notation to transform components from one basis to another. We can say a number of things of interest about these change of basis matrices, and they have to do with the fact that we are using only right-handed orthonormal vector bases. All right. Whenever we use this type of vector basis only, the matrix that relates the two bases is an orthogonal matrix, okay? And these matrices have a lot of interesting properties. The most important one is that the transpose is the inverse, okay? So this is a great aspect that we can exploit to our advantage. Whenever we need the inverse matrix, we will never have to invert the matrix, we just need to transpose it. And this clearly saves a lot of time. Just as before, we can always think of the reverse problem when we are talking about relative motion. So instead of thinking of expressing the vectors of basis 1 in terms of the vectors of basis 0 and transforming vectors as we saw before in the previous slide, we can do the same with the vectors of basis 0 in basis 1, right? So the fact that the relation between these two bases is an orthogonal matrix allows us to infer that the components satisfy this relation. So for example, the numbers that appear here are identical to the numbers that appear here, all right? So basically we have this block of 9 numbers on the left and the block of 9 numbers on the right, and they are just the transpose of each other, all right? And of course, this makes sense because these are the inverse relations with each other. Similarly, when we look at the matrix that allows us to express vector components in one basis and the other, we immediately find that this matrix, okay, and this matrix are inverse of each other. And using the property that we have over here, we can write this in terms of the transpose as well. Moreover, as the components of these matrices are essentially the numbers that appear in the expressions for these vectors, we can also say something interesting about the meaning of the components of these matrices. For example, the columns of this matrix, the matrix R01, are just the vectors I1, J1, and K1 expressed in B0. And similarly, the rows of that matrix are the components of I0, J0, and K0 in B1. Okay, so constructing these matrices is very simple, it's very straightforward. You just need to have the vector transformations here. Of course, it's the same information. Moreover, the orthogonal matrices that we have in these relations have always a set of 3 eigenvalues, okay? And these eigenvalues are, one of them is always 1, okay? And the other 2 are complex conjugate eigenvalues that can be expressed in this form. The meaning of these 3 eigenvalues is the following, okay? We can understand the transformation from B1 to B0 as a rotation, okay? A rotation transformation that brings the vector I1 into the vector I0, the vector J1 into J0, and K1 into K0. The rotation angle for this rotation is just beta, which is a number related to the eigenvalues that we have over here. And moreover, as any rotation, there is an axis of rotation, and this is defined by a vector, okay? And this vector happens to be the eigenvector associated to the eigenvalue 1, right? Interestingly, any vectors in this subspace, the subspace defined by E beta, are vectors that have components that are numerically the same in B1 and B0, okay? Essentially, if you think of the transformation matrix as a rotation, all the vectors on the rotation axis are basically not affected by the rotation, so they remain the same after the rotation. Of course, we are not restricted to using just 2 bases, and in fact, in many programs, we will define more than 2. So it's important to understand how the relations between multiple bases relate with each other. So imagine in this example that we have 3 bases, B0, B1, and B2, and imagine that we have already established the relations between bases 1 and 0, okay, either by giving the vector expressions on the left or the matrix on the right. It's irrelevant because it's the same information. And imagine that we also have basis 2 in terms of B1. So the question is, can we use this to link together B2 to B0 without passing through basis B1? And the answer, of course, is yes. We can put together these expressions. For example, we can use the first relations here to eliminate the vectors I1, J1, and K1 on the second. And if we do that, we will have the expressions that link the vectors I2, J2, and K2 in terms of I0, K0, J0, and K0. Okay. So this has been done here for the first case, okay, for the vector I2. So you see that we basically have replaced the expression for the vectors I1, J1, and K1 using the first set of relations here. And if we take this result and we gather together terms multiplying I0, J0, and K0, we will have the first relation for the transformation relations from B2 to B0. Equivalently, we can do this in matrix notation. So if we have the notation for the rotation matrices 0, 1, and 1, 2, we know that we can compose these relations. Basically, we need to plug this in here. Okay, so we replace this column vector with this expression. And what we have is an expression that allows us to compute the components in basis 0, okay, here on the left, from the components in basis 2, here on the right. The product matrix that appears here is, by definition, the matrix R02. Okay, so you see that the composition in matrix notation is particularly simple. We just have to multiply the matrices together, making sure that the inner indices are the same. Okay, so in this case, 1 has to match with 1. Okay, so clearly, what we have seen so far allows us to relate bases in arbitrary attitudes with respect to each other. In practice, we will be interested in special cases where the rotations are especially simple. Okay, in fact, we will call these rotations just simple rotations. These are rotations that occur when the axis of rotation coincides with one of the vectors of the bases. So you see the examples here. In the first case, this first drawing, we are rotating about the I0 axis. So the I1 and the I0 vectors coincide, they are the same vector. And the only vectors that change are the J and the K vector, okay? So whenever two bases are related by this type of rotation, we say that this is a simple rotation, and the relations are very simple to write down, okay? So whenever we have this type of rotation, it's very convenient to look at the rotation plane perpendicularly, okay? So if we look from the I0 axis here, we will see something like this, okay? So this is J0, this is K0, and this is J1, and this is K1, okay? And this is the angle theta x, okay? Theta x, because we are rotating about the x-axis. So using this type of diagram, auxiliary diagram, it's very easy to write down the expression of J1 and K1 in the old vector basis, all right? We just need to use some trigonometry. So, for example, for the case of J1, we can project on J0, and we see that what we have here is the cosine of the angle, and along the vertical line, we have the sine. And similarly for K0, we have here the sine and here the cosine. So writing down the vector relations is very straightforward if we do this, okay? So this would be the expressions for rotation about the x-axis, and you can see them also in the matrix form on the right, okay? Similarly, we can rotate about the y-axis. That would be a simple rotation about the y-axis, or about the k-axis, right? You have the expressions for them here and here. And just the same as before, it is convenient to look at the rotation from the axis of rotation, okay? So look at the plane of rotation perpendicular to it. Here we would look from above, right? So this is our eye. And that way, it's easy to come up with diagrams, auxiliary diagrams like this one, and get the angles right and the expressions right. Okay. Observe that the direction or the sign of the rotation is such that the rotation is counterclockwise about the axis of rotation. That is what we call a positive rotation, right? We can, of course, define the same expressions for a negative rotation. The only change is that the terms that go with a sign will swap signs, okay? So where we have a plus, we will have a minus and vice versa. My recommendation is do not memorize these expressions, okay? It's actually better to draw the auxiliary diagram every time that you have a rotation, and you can very quickly infer the expressions that you need. This is actually better because in some cases we are using negative angles, or perhaps the case is not so trivial, and if you just want to remember a given expression, it may not apply for all cases. So it's actually better to derive the expressions every time that you need them. Simple rotations are particularly useful because they allow us to describe any complex orientation, okay, no matter how complicated your attitude. It can be described in terms of 3 sequential simple rotations, okay? So this is what gives rise to what we call Euler angles. So imagine in this example that we want to describe the blue basis over here, basis number 3, in terms of the basis 0. So clearly the attitude, the orientation of basis 3 is quite complex with respect to basis 0, but this is not a problem because we can reach that attitude by concatenating 3 different rotations, 3 different simple rotations. So let's start, for example, by rotating about the vertical axis, K0, by an angle psi. So this is basically the expressions that you have in the previous slide. And this rotation brings the basis 0 into a new auxiliary vector basis 1. All right. So basis 1 is defined in terms of this auxiliary rotation. Then we can continue the process by taking this auxiliary I1 axis that we have defined from the previous rotation and rotating again about it. All right. So this is a rotation about the I1 axis, which brings the J and K vectors of our red basis into the basis number 2. Okay. A new auxiliary vector basis that we have defined in this way. Let us call the rotation angle in this case theta. And finally, we can reach our destination, the basis number 3, with a last rotation. And in this case, why not? Let us rotate about the third vector again. Okay. Observe that this vector, we are rotating about k2, is different from the original vector k0. So in this case, we call the rotation angle phi. All right. So if you think of these 3 rotations in terms of matrix notation, each of them has one matrix, right? So of course you can compose them and obtain the matrix for the compound rotation by multiplying them together in the right order. All right. The angles that we have defined in this way with these rotations is what we call the Euler angles, and they have a special name. So the first one, psi, is what we call the precession, theta is what we call nutation, and phi is what we call spin, right? These are known as the standard Euler angles, all right? And you see that we have defined them in a particular way. We have chosen the order of the rotations to do this procedure. This is also called the 3-1-3 Euler angles for this reason. Okay, you see we have rotated about the third axis, the K axis first. Then we have rotated about the first axis, axis I, and finally we have rotated about the third axis again. All right. Observe that the rotations occur in a sequential manner, so each rotation uses the last vector basis that you have defined as the starting point, right? Well, clearly, we can define many other types of Euler angles, and they are actually useful in given different situations. In particular, a common choice is also the 3-2-1 Euler angles, all right, where The first rotation is the same one as in here, but then we rotate about the J1 axis, and finally we rotate about the I2 axis. Of course, the value of the angles will be different to reach the same attitude, and the name that we give the angles in that case is the yaw, pitch, and roll angles. Okay, this set of Euler angles is used quite commonly in flight dynamics. You can create any sort of Euler angles. The only rule that you need to remember is that you cannot repeat the same axis in sequence. Okay, so for example, if you try to do 3, 3, 1, this is not valid because you are rotating twice about the same axis, and clearly this is the same as if you just did one rotation about the third axis. So this is not a valid choice. Okay, however, 3, 1, 3, as we have seen over here, is a valid choice because between the first 3 and the last 3 we are doing different rotations. So the axis K2 and the axis K0 are different directions in space. In that case, there is no problem. See this with an example. So imagine that we have two reference frames. The red one is R, which here is attached to this space shuttle model for visualization of the rotations, and a blue one, which you can see over here as well. So the red reference frame will be at any arbitrary orientation, any arbitrary attitude with respect to the blue one. So how can we describe it with 3 Euler angles? Well, we will perform 3 sequential rotations starting from this situation where the reference frames are coincident. Okay, so in this example, since it's basically a flight dynamics problem, we are going to use the 3, 2, 1 Euler angles, and as you can see, we have oriented our reference frames in this particular manner. So the x-axis is pointing forward, the y-axis is pointing toward the right wing, and the last axis is pointing downward. Okay, so this is a right-handed vector basis, and this is the common choice for many flight dynamics problems. So the first rotation happens about the third axis. Okay, so that is the KB vector, and this introduces the auxiliary vector basis 1. So KB and K1 coincide while I1 and J1 are different. The expressions for the rotation are just those that you see over here. They are the same as what we saw in a previous slide. The angle of rotation, let us call it psi. Okay, so this is the angle psi, like that. We continue with a rotation about the second axis, okay, the y-axis, and this brings us to the second auxiliary basis, basis 2, and the angle of rotation is theta. Okay, so that is the expression that you would use in this case. And finally, to reach the final orientation, we would rotate about the x-axis. So imagine that the final orientation in this particular example is that one. Okay, so the shuttle is flying in that particular position. So that rotation happens about the I2 axis. The expressions are over here, and the last angle is the angle that we call phi. So it's important to remember that Euler angles are not unique. There are many ways of defining them. And moreover, even if you choose a particular type of Euler angles, such as 313, each attitude can be defined in different ways with different values of the angles. There are even some attitudes that are what we call singular, okay, where two of the angles are not well defined. This type of problems will appear more evidently when we move on to the second part of the course about rigid bodies, so we will discuss them there. Okay, so let us continue with the next part of the lecture, which has to do with angular motion. Okay, so in this case, we are not concerned about the instantaneous attitude of two vector bases, but on the contrary, how this attitude changes in time. Okay, how this orientation changes in time. All right, so again, what we need to do is to provide the expressions that give the vectors of one basis in terms of the other, but now as a function of time, okay? What we will see is that this can be reduced to given one vector, which expresses how the vector basis is rotating at each instant, okay? This is what we call the instantaneous angular velocity, all right? And we are going to use this nomenclature, all right? So for example, when we are talking about the rotation of a reference frame 1 with respect to a reference frame 0, we will use the nomenclature like that, okay? Now this vector has, as always, as any vector, direction and magnitude. The meaning of the direction of the vector is the instantaneous axis of rotation of the basis b1 with respect to b0, okay? So it doesn't tell us what is the instantaneous attitude of the basis, but it tells us how it is changing in time, okay? And the magnitude also tells us the angular rate, how quickly the rotation is taking place, okay? Now, as I mentioned here in this red box, observe, just as a reminder, that the angular motion and the translational motion are totally unrelated, okay? So regardless of what the origin is doing, okay, even if the origin is stationary or if it's moving somewhere with any velocity, whatever, what we are discussing here is just the angular motion, okay? So for that purpose, you can completely ignore the motion of the origin. You can plot the vector basis with the same origin and discuss the angular motion there. So how is this angular velocity vector useful? Well, it is useful because what we will want to do is to discuss the rate of change of the vectors of one basis, okay, basis 1, in terms of the basis 0, okay, in reference frame 0. So the angular velocity vector helps us to do that in a very simple manner. We just have to take the cross product between omega and each of the vectors of the basis, and that gives us the derivatives that we are interested in, okay? These expressions are the type of expressions that we will use continuously when solving the kinematics of point particles later on. So we basically need to know how the vectors of the basis are changing. Now, this is also useful because if you give me any vector, for example, vector c, which is constant in the reference frame S1, okay, so imagine that you have here your reference frame S0, and here is your reference frame S1, and you have a constant vector in S1, okay, this is vector c. Now, c is constant in S1, so its derivative in S1 is 0. But if S1 is rotating with respect to 0, the vector c will have a derivative in 0, which is what we want to calculate here, all right? So basically, we just have to enter the expression of c in basis 1 and take derivatives there, okay? So we have 3 different terms, so we apply the rules of differentiation and take into account that the components in that basis, in that particular basis, are constant, okay? So we just need to consider the derivatives of the vectors of the basis, which appear here. Now, from the expressions above, we can replace those expressions in terms of cross products with the angular velocity vector, omega 1, 0. Reordering these cross products, you can write it like this, and finally, you see that you can more compactly write the derivative of this constant vector in this way, okay? So the expressions that we just saw for the vectors of the basis are not only good for the vectors of the basis, but for any other vector that is constant, okay? The derivative in 0 of a vector that is constant in 1 is just this rotational term that involves the angular velocity, okay? Observe in particular that, of course, the vectors I1, J1, and K1 are constant vectors in 1, okay? So the rule applies as well there. So before we continue, we are going to define also the derivative of the angular velocity vector, all right? And this is what we will call the instantaneous angular acceleration vector, all right? Observe again the nomenclature. We use 2 subindexes to refer what reference frame is rotating with respect to what. okay? And more importantly, observe that in the definition, we are taking the derivative with respect to the last index, okay? So this number here and this number here have to match if we want to call this derivative an angular acceleration vector, okay? If you just take the derivative of omega 10 in a different reference frame, for example 2, this is no alpha of any type, okay? So remember that these numbers have to match. Now, this is a new vector, okay, alpha, which tell us how the vector omega changes in time. So all the things that we have discussed about the derivative of vectors so far also applies here. If we consider, for example, the reference frame S1 in red and the reference frame S0 in black, imagine that the instantaneous angular velocity is this particular blue vector over here, and that the instantaneous angular acceleration is this orange vector. So what does it mean for the evolution of omega? Well, we can decompose alpha in two components, a parallel component to omega and a perpendicular component to omega. The parallel component is related to changes in magnitude of omega, and the perpendicular component is associated to changes in direction, okay? So of course, alpha and omega do not need to be parallel. They can be anything, but the parallel and the perpendicular component have a clear interpretation, as with any other vector and any other derivative, okay? So as I say here in these boxes, observe that the particular direction and magnitude of omega has nothing to do in general with the instantaneous attitude of the red reference frame, okay? So the red reference frame can be oriented in any way, okay? And the omega vector can be in any direction, okay? So the instantaneous attitude is given by the orientation of the basis, but how this attitude is changing in time is given by omega. And what I just discussed about the two components of alpha projected in the parallel and in the perpendicular direction to omega are what I discussed here in these boxes. Okay, so let us consider one example. Let us focus on a simple rotation, such as the one that you see here. We are rotating about the third axis. These are the expressions of the change of basis. But let us consider that now the angle changes in time. Okay, so the expressions have to consider that this is a function of time. Now, we can compute the derivatives of these vectors in basis B0, okay, and we can do that like this. So let me just consider the first one, for example. Okay, so if we take derivatives here, we are taking derivatives in vector basis 0, so I0 and J0 are constants, so the only things that change are the cosine and the sine. So we have minus psi dot sine psi I0 plus psi dot cosine psi J0, okay? Similarly for J1, you have this, okay? So minus psi dot cosine psi I0 minus psi dot sine psi J0. That's just taking derivatives there. Can we identify here in these new expressions the vectors of the old, the vectors of the new basis, the vectors I1 or J1? Well, certainly yes. For example, in this first expression, this and this, with the minus here, okay, those are basically the components of J1. So a different way of writing this vector is just by saying that this is equal to psi dot J1. Okay, the derivative of I1 is psi dot J1. And this makes sense with the type of things that we already know about these vectors and their rotations from previous lectures. So as psi increases, I1 is going to move in this direction. Okay, so this is the direction of J1. And the rate of change of I1 has to do with the rate of change of the angle psi. Similarly, we can do the same thing for the second expression, and we have here minus cosine minus sine. This is basically the negative of I1, so we can write the second derivative as psi dot with a minus I1. Okay. Again, we can see this in the diagram. The way that J1 changes is the minus direction of I1, and again, its rate of change is, of course, related to the angle psi. Okay. So we get these expressions by taking derivatives. Of course, if you try to take the derivative of the last vector, you just get that it is equal to 0. All right. So the question is, what is the angular velocity vector in this case? Well, it must also hold that these expressions can be used to compute the derivatives of the vectors of the basis. Okay. So let us try to see if we can propose a valid angular velocity vector that gives us these results without having to take derivatives in the change of vector expressions. The answer is yes, of course. If you define your angular velocity vector with the magnitude of the rate of change, psi dot, and the direction of the rotation axis, k0, you observe that this indeed satisfies the relations here. Okay, so if you take the cross product of this omega defined in this way with I1, the result is of course psi dot J1, as we obtained by taking derivatives. Okay, so it makes sense. If you take the cross product of omega with J1, you get minus psi dot I1. And if you take the cross product of omega with k, you get a 0 because the two vectors are parallel. Okay, so this is the behavior that you would expect. So this is the way that you can postulate the angular velocity vector of a simple rotation. It's always the same, and it's worth remembering this. The magnitude of the angular velocity vector is the rate of change of the vector. Okay, in this case is psi, so we have psi dot, and the direction is the direction of the axis of rotation. All right, so here we were rotating about k0 in the positive sense. Okay, so the vector is k0. This is true for any other rotation. So when you rotate about the I axis, you will have the I vector in omega and so on. Okay. All right, so let us take a look at the last topic of the day, which is the Coriolis theorem. Okay. Now imagine that we have a vector b, which now is not constant in a reference frame S1. Okay, so let us take a small drawing here. Imagine this is S0, we have S1, okay, which may be translating and rotating with respect to S0. And now we have a vector b, which is a function of time in S0, okay? So if we have b written in this way, okay, already expressed in basis 1, it is quite straightforward to take the derivative in basis 1, okay? In this case, the vectors I1, J1, and K1 are considered constant, so the derivative is just the derivative of the components, as you see over here, right? So this would be the derivative in basis 1. But the question arises, what is the derivative in basis 0? So again, we go back to this expression, okay, and we apply the rules of differentiation. So when we have a product, we have to take the derivative of each of the components separately, okay? And we must not forget that the unit vectors may have a derivative. And this is the case when you are taking derivatives in a different reference frame. I1, J1, and K1 do not need to be constant, okay? You must consider in general that they have a derivative. So you can write these expressions, this derivative in this way. On the one hand, we have exactly the same as we had before, so we can identify this with the derivative of b in 1, okay? But new terms appear in the derivative of the vector in reference frame 0, which are related with the derivatives of the vectors of the basis 1, okay? after some algebra, you can rearrange this in the following manner. So basically, you see that you have the components of the vector untouched, okay, so they didn't change. But you have the derivative of the vectors of the basis, which we can write down in terms of omega. So this can eventually, after some algebra, be expressed as omega cross b. Okay, so indeed, this is what we have here now. So this is the relation between the derivatives in vector basis 0 and vector basis 1. Okay, you see that the two derivatives are essentially the same, except for this rotational term that appears on the right-hand side. This is what we call the Coriolis theorem, all right? And it allows us to put into relation the variation of a vector that one observer sees with respect to the variation that another observer sees. Okay, so this is essential for the relative motion. When we want to relate two different descriptions of motion from two different reference frames, we will have to make use of this connection between the derivatives of vectors in different reference frames. Now, remember that any vector can be defined with respect to one reference frame. For example, here we have assumed that B is a vector with an origin on S1, assuming that the origin is important for this vector. Many vectors are free vectors and we can draw them anywhere, okay? But we can take the derivative of a vector in any reference frame, okay? So we can define them in any reference frame. We can take the differential of the vector in any other reference frame, and still we can express the vector in any other vector basis, okay? So it's important to keep this in mind. This vector expression here, the Coriolis theorem, is a vector expression. When we want to compute this expression, we can choose to write it down in any vector basis, okay? So nothing stops us from using, for example, vector basis 2 to write down these three vectors. This is a vector, this is a vector, this is a vector. So we can choose any vector basis to express any vector, all right? So don't forget that, and don't confuse the vector basis that you use to express a vector with the reference frame in which you take derivatives or anything like that, okay? They are separate concepts, and you can mix them in any way. So let us consider this example. Imagine that we have this vector which is expressed in vector basis 1, and clearly it's not constant in reference frame 1 because the components depend on time. Imagine, moreover, that S1 and S0 are related by this simple rotation, the same one that we had before, all right? So let us see how we can compute the derivatives of B in one reference frame and the other. So let's start by the simpler one. So the derivative of B in reference frame 1 is particularly simple because we have the vector already expressed in vector basis 1, so we don't need to consider the derivatives of the vectors of the basis. So we just have I1 plus 2t j1 plus 3t2 k1. That would be the derivative with respect to vector basis 1. What is the derivative with respect to vector basis 0? Now, there are many ways to do that, okay? So in this example, I want to bring your attention to that. We can, of course, use the Coriolis theorem that we just saw before, okay? So in this case, this is a simple rotation. As we saw, the angular velocity vector is just psi dot k0, okay? So using the Coriolis theorem, we can write this derivative as the derivative in 1 plus omega 1 0 cross b. Okay, so hopefully we can compute this in a relatively straightforward way. So let me compute this on the margin. So we write this in vector basis 1, okay, like this. So omega, I have written omega here in basis 0, but of course k1 is the same as k0, so we can write it in basis 1 like this. So for the purpose of this cross product, the components in 1 are just 0, 0, psi dot. And finally, the vector b is t t squared and t cubed, like that. Okay, so if we take this determinant, what we have is psi dot t squared 1. Okay, then we have with a minus, sorry, and then we have plus psi dot, oh my god, I'm sorry, let me start over because I'm mixing things and getting ahead of myself. So yeah, this was correct. So minus psi dot t2 in the direction of I1, and then we have plus psi dot t j1, and that's all there is. Okay, so your cross product, so your derivative in 0 now reads like this: 1 minus psi dot t squared in the direction of I1 plus 2t plus psi dot t in the direction of j1 plus 3t squared k1. Okay, so clearly this is one way of computing the derivative in the other reference frame. What could we do instead? So one possibility would be to use these expressions to replace I1, J1, and K1, so we can write B in basis 0 and then take derivatives in that expression. That way we don't need to apply the Coriolis theorem because we already have everything in basis 0 and it's easy to take derivatives directly. So that can be done, of course. Let us see that we have the same result. So we take B, we have to replace I1. So we have t cosine psi I0 plus sine psi J0. Okay. Then we have t squared, which is now in the direction of J1, which is minus sine psi I0 plus cosine psi J0. Sorry. Okay. 0. And finally, we have t3 k0, which is the same as k1. So we can take derivatives here, okay, in reference frame 0, and the result should be the same one as before, okay? Let us check that indeed this is the case. So I'm going to gather together the terms that depend on I0. So I have one here and one here, all right? So when I take derivatives with respect to time, I get the derivative of t gives me 1 multiplied by the cosine, so I get cosine psi. Then I also have minus t psi dot sine psi when I take the derivative of this cosine. Then moving on to this other term here, I have plus 2t with minus sign, so this becomes minus. And then the derivative of the sine gives me psi dot cosine psi. So all this goes in the direction of I0. Okay. Let us continue with the same thing along J0. So here we have terms along J0. Sorry, because I realized that this parenthesis shouldn't be here. The parenthesis should be here. Okay. So when we take derivatives, now for these terms, we have, let me continue here, sine phi, when I take the derivative of this time, plus t psi dot cosine psi. And then moving on to the second parenthesis over here, I have plus 2t cosine psi minus t squared psi dot sine psi. Okay, and all this goes in the direction of J0. And finally, for K0, that's easy, we have 3t squared K1. So how is this the same as this expression here? Well, it is the same if we have not made any mistakes. The only thing is that this is the result expressed in basis 0. Okay, so how can we check if the result is the same? Well, we need to convert either these vectors to vector basis 0 to see that the results match, or we should identify vectors in this expression to see that they can be reduced to vectors I1, J1, and K1. So clearly K0 is K1, so there's no problem there. Let us see if we can summarize this somehow and find relations between this expression and the other. So for example, if I gather together this term and this term, okay, I have cosine psi I0, sine psi J0, that gives me I1, okay, so that explains this one over here. Okay, that's good enough. Let us see if we can create this term over here, the minus psi dot t squared. So that is associated to this term and this term. And again, we see that, yes, if we add them together, we have cosine psi, sine psi, that gives me I1. So they correspond. So this is okay. All right, so they are the same vector. Let us now see about the other two terms that we have over here. So let me use a different color, purple. Okay, so how about this one? So this has to come from here and here. So are they the same? Well, yes, because we have minus sine psi plus cosine psi, and this is just the J1 vector. Okay, so when we gather these two vectors together, we get this. Okay, and the final term is of course related to this and this, and again you see that we have minus sine plus cosine, so that is J1, and that corresponds with this. Okay, so yes, these two expressions are the same, and you have seen two different ways of computing the derivative in reference frame 0, either by using the Coriolis theorem. Okay, and that means that you need to compute a cross product. That's fine, but you need to compute the cross product. Or by moving everything to the basis 0 and taking derivatives there. It's perhaps, you avoid the cross product, that is perhaps more cumbersome because the result will be in basis 0. And if that's what you want, that's fine. But quite often you want the result in basis 1. So then you would need to convert back to basis 1. Okay, the important point is that the two methods yield the same result, of course. So one thing that we have not yet discussed is the relation between angular velocities when we have more than two reference frames. Okay, so this is what we call the composition of angular velocity vectors. So imagine that you have a reference frame S2 that is rotating with respect to a reference frame S1, and its rotation is given by the angular velocity vector omega-2,1. At the same time, S1 is rotating with respect to S0 with an angular velocity omega-1,0. Now the question is, what is the angular velocity of reference frame 2 with respect to reference frame 0? Well, the case is, the rule is quite simple. We just have to add together the angular velocities, okay? So you just have to compound them in this way, all right? If you do, you get the velocity, the angular velocity of 2 with respect to 0, okay? This can be proven as an exercise if you write down the transformation relations for the vectors of basis 2 with respect to the vectors of basis 1, and similarly the relations for the vectors of basis 1 with respect to the basis 0, and you take derivatives there to find the angular velocity vectors, okay, you should find omega-2,1 and omega-1,0. If you use those relations to find the relations between the vectors of basis 2 with respect to the vectors of basis 0 directly, and you take derivatives there, you should be able to find that the angular velocity of the compound rotation is the sum of angular velocities. Okay? Now, this is the rule for the composition of angular velocities. The composition rule for angular accelerations is a little bit more complex, all right? So let us start by taking derivatives with respect to reference frame 0 in this relation, okay? So if we do that, we can identify here the angular acceleration alpha to 0, okay? Because this number and this number match. So that's our definition. And similarly, here we see alpha 1, 0, because we have 0, 0. But the term in the middle is a little bit more complex. So if we apply the Coriolis theorem to this derivative, okay, so we can relate it with the derivative in 1 by adding this extra term, then we see that now, yes, we have 1, 1, so this is alpha to 1, okay? So finally, the rule for the composition of angular accelerations is a little bit more complex. You see the sum of the two alphas, but you see this extra term, which is due to the combined product of the rotations. Of course, we can always think of the reverse relations in relative motion. So if imagine that you only have now S1 and S0, and you already have omega 1, 0 and alpha 1, 0, and you wonder what are the reverse relations, so omega 0, 1 and alpha 0, 1. Well, the relations in that case are quite straightforward. You just have that they are opposite with respect to each other. To conclude this lecture, I want to take a look at the angular velocity of an arbitrary rotation in time expressed in terms of Euler angles that depend on time. Okay, so this is particularly useful for many problems. When you have an arbitrary rotation, usually the route to describe it in the kinematics is to introduce three Euler angles that depend on time that are part of your coordinates of the problem, okay, and then find the angular velocity and acceleration associated to them. So imagine that we have the same order of rotations as we saw before. Okay, so this is a 3, 1, 3 type of Euler angles. Okay, and we have this composition of rotations. The only difference is that now the angles depend on time, so they have an associated angular velocity. So for the first rotation, you have this rotation about the third axis of an angle psi. So you can write it as psi dot k0 for the angular velocity. Of course, this is the same as psi dot k1 because the vectors coincide. For the second rotation, likewise, you have theta dot I1, and for the third rotation, you have phi dot k2. Now, what is the angular velocity for the global rotation, for the combined rotation? Well, that is the angular velocity 3, 0, okay? The rotation of basis 3 with respect to basis 0. Using the rule of composition of angular velocities that we saw before, we just need to add together the three angular velocities that we have identified to get this result, okay? So that is the angular velocity of the combined rotation. Now observe that I have written this vector using unit vectors of different bases. So I'm combining vectors of basis 2, basis 1, and basis 0. Is that a problem? Is this incorrect? No, it is perfectly correct, okay? Again, I have recovered this box from before and expanded it. Remember that any vector can be defined in a reference frame, it can be differentiated in another, and it can be expressed in yet a different one, okay, in a different vector basis. What is more general, we can always express any vector basis, any vector, we can express it as a linear combination of other vectors, okay? So any vector, for example, omega 3, 0 here, can be expressed as a linear combination of other vectors, regardless of whether these vectors are unit vectors of some bases. If all the vectors are in the same basis, that doesn't matter, okay? This result is correct. Another question is if this result is practical. Well, it is to some extent, but usually we want to work with vectors expressed in a single vector basis because that is more convenient to us when we want to take cross products and operate with the vectors, etc. It is more convenient if we have already expressed them in a single vector basis to be able to operate. So this is what we can do, what we do in this slide. So this is the result from the previous slide. If you use the expressions to convert K2 and I1 into vectors of basis 0, eventually you will get this result. Okay, so this is the expression of omega 30 expressed in vector basis 0. This is useful for many problems, but in some cases, it will be more interesting to work not in basis 0, but in vector basis 3. So you can do the same thing in reverse. Instead of converting everything to basis 0, you convert these three vectors here to basis 3. Okay, so when you do that, you get this result. You see that the result is different. Of course, the components are numerically different, but the vectors are, of course, the same. It's just that we are expressing them, this vector, in different bases. Okay. Now, as an exercise, you may want to try to do this exercise to try to express the angular velocity vector for the 3 to 1 Euler angles, assuming that the angles depend on time. Okay. So that's it for today. In the next video, we are going to continue with this topic, and we will learn about the kinematics and the dynamics of relative motion. Thank you, and see you next time.